A. Cultural aspects of health, health services, health institutions, health problems and health practices prevailing. B. Modes of production. C. Social structure. D. Distribution of power and political organizations, and A. Mobilization of resources and pattern of their uses within the community in the context of cultural perception and cultural meaning of the health problems. 1.8 Summary. In this unit we have studied application of social sciences in health. This gives us insights into social sciences and how these are used to understand human behavior and human society. We have understood how and why nurse should know about application of social sciences. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.
Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Computer and Information Sciences, SOCIS, Diploma Program. Bachelor's Degree Programs. Bachelor of Computer Applications, BCA. Semester 4 BCS-040 Statistical Techniques. Block-1 Statistics and Probability. Unit-1 Descriptive Statistics. 1. Introduction. Most of us associate statistics with the bits of data that appear in news reports, cricket, batting averages, imported car sales, average high temperature on a particular day etc. Advertisements often claim that data show the superiority of the advertiser's product. The word statistics, which is derived from the word state, entered the English vocabulary in the 18th century. It was used then, and still is used, to mean one or more sets of numerical data on various items like population, taxes, wealth, exports, imports, crop production, etc., which are of interest to state officials. There are two ways to use the word statistics. If we say, statistics is, we are generally referring to the science of statistics. If we say, the statistics are, we are referring to numbers such as batting averages, the number of unemployed during the month of October, or the number of deaths from malaria during a given year. It is hard to come up with a concise definition of statistics because it is a broad subject that has many facets. Commonly, it is believed that statistics involves the collection, organization, analysis, and interpretation of data. There are several reasons why the scope of statistics and the need to study the subject. Statistics have grown enormously in the last 50 years. One reason is the increasingly quantitative approach employed in all the sciences, as well as in business and many other activities which directly affect our lives. This includes the use of mathematical techniques in the evaluation of anti-pollution controls, in inventory planning, in the analysis of traffic patterns, in the evaluation of teaching techniques and so forth. The other reasons are that the volume of data that is collected, processed and disseminated to the public for one reason or the other has increased almost beyond comprehension. More and more persons with some knowledge of statistics are therefore needed to take an active part in the collection and analysis of the data, as also in all of the preliminary planning. One question that naturally arises at this stage is why and how such large volume of data should be collected, organized and analyzed? We shall address such questions in this unit. We shall begin by discussing the need for collecting data. We shall then talk about different types of data and the ways of arranging them to obtain any logical conclusions from them. Graphical methods of presenting data are also discussed. Finally, we shall discuss various measures that are commonly used to summarize information contained in a data set. Objectives. After studying this unit, you should be able to organize the given set OT data in a meaningful way. Construct a frequency distribution of a variable from a given set of data. Represent graphically a frequency distribution of a variable and interpret the information suggested by it. Obtain the average level of a given set of data where its frequency distribution is centered by calculating its mean, median or mode. Obtain the degree to which TLE individual measurements in a given data vary about this average by calculating its variance and standard deviation. 1.2 Collecting data. We start with a few examples which provide you a general idea about situations where we need to handle a large amount of data and where statistics can play a significant role. In these examples, we try to raise issues which can be handled adequately by the various statistical tools with which we will be introduced to as we go along in this course. Example 1. Suppose we are in the process of drawing up a comprehensive plan for developing public medical facilities in a big city. To work out the rates to be charged for various services proposed to be offered by the hospitals to be set up under the plan, it is necessary to know the economic conditions of the 1 million households constituting the entire population of the city. For this purpose, we need to divide the households, which are the individuals about which information is sought, into 3 broad categories: high income group, HIG; middle income group, MIG; a mid-low income group, LIG, according to certain criteria. How do we proceed? Obviously, it would appear as if the task would involve visiting each of the 1 million households to inquire about, say, their monthly incomes. What are the issues and difficulties in implementing this proposal? There are many. For instance, A. Visiting 1 million households, and in many cases, repeat visits may have to be made following non-availability of respondents at the time of visit, is a time-consuming affair and we may not have enough time at hand. B. To cover such a large number of households, we may have to employ a very large number of investigators and that will mean a lot of expenditure. C. Even if we are in a position to afford the time and money that we need to cover all the households, 2 more issues crop up. I. As the survey may take a long time, the figures on monthly income of households covered in the beginning of survey and those of the households covered later may refer to different time periods. E. The data that we will be collecting will be a series of 1 million figures and obviously such a series as it is will hardly make any sense. We would need proper methodology to properly compile, to analyze and to interpret the data, so as to make some sense out of these. In view of A and B, it seems that the process of complete enumeration of all households will not be really efficient and we will have to think of an alternative procedure. To obviate difficulties mentioned in A and B, we might consider only a subset of the population, viz., a sample of households, and collect information on I here earnings only. Then try to use the fractional information thus collected to make a guess about the actual state of affairs pertaining to the totality of households. Now, of course, this method will reduce the cost and time required for the survey and we will have a shorter series of figures. However, issues enumerated in C remain to be handled. Moreover, several other new issues like the following would come up now. DL. How do we select our sample? A. How do we relate the sample field links to the state of affairs I, irrespective of the entire population of 1 million households? F. Also, even if we are in a position to make such an assessment on the basis of the information contained in the sample, how much reliability should we attach to it? Since after all the assessment is based on our observations in a single sample which is perhaps comprised of a small portion of the totality, and the same could be quite different if we had a different sample. This aspect surely introduces an element of uncertainty in our conclusion, as different samples may differ in respect of their information contents and thus may lead to different conclusions relating to the same population. EIOW. Do we handle the situation then? Thus, though the problem initially looked rather simple, the issues involved are not so. By any standard, solutions of such issues come under the purview of statistics. The population, i.e., the totality of households in the above example, is finite and observable. However, often the population is neither finite nor physically existent. Rather, it may only be conceivable or hypothetical. Example 2. Consider a system where customers arrive at a counter for service. Customers may be patients coming to a clinic for medical attention, or may be aircrafts waiting for clearance from the air traffic control to take off, or even broken down machines in a factory waiting for the attention of an operator, and so on. Our objective is to prescribe a policy so that congestions can be avoided. However, neither the number of AMBULs is fixed on all occasions, nor is the service time the same for all customers. These are usually uncertain and thus subject to chance factors. How do we then propose to proceed? Example 3. Suppose a new brand of pain reliever has been marketed recently. The manufacturer claims that it relieves pain 25% time faster than any of the comparable brands already available in the market. How do we propose to verify this claim? Obviously, we have to administer these drugs to a sample of individuals. But then how should the sample be chosen? Also, individuals may react differently to the same drug. How do we take this IILTO account? How do we process the sample data? Finally, the good old question, to what extent can we generalize our sample findings so as to be able to come up with a conclusion pertaining to the entirety? How reliable is the sample finding in this case? Example 4. The yield of a certain crop is dependent on the location of the plot, amount of fertilizers applied, amount of rainfall, availability of irrigation facilities, etc. However, it is also known that even when all these factors are applied equally, the yields may still vary. This is so because the factors we listed may not exhaust all the factors that influences the yield. Many such examples may be cited to illustrate the areas of application of statistics. However, it will be gradually apparent that the basic issues involved in these illustrations are similar and can be discussed within a broad framework, and this framework is provided by statistics. To study a given phenomenon, the basic raw material would be data, information relating to it. For example, to study the growth in the use of telephones, we may collect the number of telephones that several workers install on a given day, or that one worker installs per day over a period of several days. These figures then constitute our data for studying growth in the use of telephone. Observation before it is arranged and analyzed is called raw data. For data to be useful, our observations need to be organized so that we can pick out trends and come to logical conclusions. We shall thus discuss the techniques of arranging data in tabular and graphical forms to be able to make genuine sense out of it. First, we shall start with describing different kinds of data. Cite at least 2 examples from your own experience illustrating the application of statistics. 1.2.1 Kinds of data. The operation of collection of relevant data comes in the initial phase of any statistical study. Data relevant for a study can be obtained either from published works or from the collections of the government or research organizations, or through direct fieldwork. The mode of collection of data and the methodology for analyzing the same comprise the core of statistical discipline. Statisticians gather data from a sample. They use this information to make inferences about the population that the sample represents. Thus, sample and population are relative forms. A population is a whole, and a sample is a fraction or segment of that whole. Whenever the data are numerical, then the corresponding characters are called variables. Thus, the number of items failing to meet specifications in a lot of 100 items, the daily number of customers visiting a particular shop, the line number of telephone calls received by an operator, the life, in hours, of an electric bulb, etc. are all examples of variables. In some cases, however, the data may not be numerical in nature. This will be the case when, for example, one is examining a lot of manufactured items and classifying them as either good or bad. Similarly, if each member of a group of individuals is asked to say yes or no, according as his monthly income is at least 5,000 rupees or less than 5,001 rupees a month, the resulting data will not be numerical. This exercise will produce only a series of yes, S and no, S. However, in both these instances, the data are easily convertible to numerical terms. For instance, in the last example, we may code a yes as 1 and a no as 0. Such characteristics, e.g., quality of manufactured items or the salary position, are called attributes. You may note here that in the first three examples given above, the variables take on only some isolated values, for instance, the number of items failing to meet specifications in a lot of 100 items can be 0 or I. Or at most 100, i.e., a whole number between 0 and 100, and never a figure like 3.7, say. Such variables which take on only isolated values, which are often integers, but need not be such always, are called discrete or discontinuous variables. This kind of data result from counts and therefore values jump from one point to the next with no possible measures in between. On the other hand, certain variables are such that they may take on any value along a suitable scale. For instance, the distance, in meters, between 2 points, in the interval between 210.5 and 320.6 can take any value like 210.56, 210.687, 315.685 and so on. Such variables are called continuous variables. Variables representing height, weight, age, time to complete a journey, temperature etc. are all of this variety. Although continuous data can take on a theoretically infinite number of possible measures, the values that we use in practice are determined by 1. The precision of our measuring instrument and 2. How precise we need to be. For example, if you measure the length of a newborn baby, you would record it as 48 centimeters, 49 centimeters, etc. For most practical purposes we will not be required to measure a baby's length to the 5th decimal place. We now present some data to illustrate the concepts of attributes and variables. Example 5. The following table is a summarized version of data relating to the educational background at graduation level of students admitted in the MBA program of a certain college. Here the educational background of students admitted is an attribute which can be either arts, science, commerce, engineering or any other branch. Example 6. The following table gives the raw data relating to the marks, out of 10J, of 100 students in a statistics examination. Here the marks in the test is a variable, which varies from one student to another. Since the marks are in whole numbers between 0 and 10, it is a discrete variable. The data in the given format is called ungrouped data. The way the marks have been reported does not help us in knowing who scored how much. Perhaps that is not important f tilde the purpose of the study at this stage. We are interested in knowing how the performance was in general. Was the test very simple in the sense that a large proportion of students scored high marks? Was the test too difficult in the sense that a large proportion of students scored very low marks? It may not be easy for you at this moment to answer such questions with the data available. To respond to such questions, we have to present the data in an organized manner. We shall take up this example again in the next section and try to find answers to the above questions, but before that, let us look at the data corresponding to continuous variables. Here the life of a bulb is a variable which varies from one bulb to another. In this example, the figures have been recorded correct to 1110th of an hour. All values larger than 511.55 but not larger than 511.65 have been approximated and represented by 51.1.6. Although, conceivably the life could be any value on the continuous scale from 0 to infinity, the limitation on the part of the measuring instrument invariably imposes an artificial discreteness in the data. This is due to limitations of measuring instruments. For instance, in this case the scale could measure only up to the first place of decimal, but if we had a scale which could measure up to, say, 5 places of decimals, the accuracy would have increased. No matter how fine the scale is, one would have to stop after a finite number of places after the decimal point, and as such a discreteness would anyway creep in. But, theoretically, the variable under consideration is continuous in character, as it can adopt any value over a specified interval, finite or otherwise. Let us now see how the raw data in examples 6 and 7 can be arranged to obtain any logical conclusion from them and obtain an answer to the questions asked here. Via 1.2.2 frequency distribution of a variable. From the data in example 6, for instance, it is not possible to readily answer questions like how many students scored 3 and above, or how many of them scored between 5 and 7, or what is the score obtained by most of the students. It will be easier to answer such questions if we compress the data in the form of a table 4 given below. Here we put a tally mark against a score as soon as we come across the same as we go along the list. Data, in any n order. For instance, if we read the data column Y*, first entry in first column is 2, so we put a tally mark against 2 as shown in table 4. Number of tally marks against 2 indicate the number of students getting 2 marks. You may observe here in this table that every fifth tally is a slash over the first 4 tally marks. Finally, we count the tallies for each variable value, i.e. score, to obtain the number of times it appears in the data set. We call this number the frequency of the variable. Definition: the frequency of any value occurring in a data set is the number of times the value occurs in the set. Once we know the frequency with which the values occur in a data set, we can construct a table showing the frequency of each value against it. We call this table a frequency distribution. Table 5 gives the frequency distribution for the data set in example 6. An entry in the second column gives the number of students receiving the corresponding score that is depicted in the same row under the first column. Thus, there are 10 groups, classes or categories, in the table above. Each group corresponds to a single value of the underlying variable. Note that the third column gives the proportion of students receiving the various scores called the relative frequency of the value. Definition: relative frequency of a value occurring in a data set is the frequency of a value as a fraction or a percentage of the total number of observations. Now suppose we want to see how many students got less than 6 marks. Then we have to add up the frequencies of 0, 1, 2, 3, 4 and 5 marks to obtain the number of students getting marks less than 6. Then we have to add up the frequencies of 0, 1, 2, 3, 4 and 5 marks to obtain the number of students getting marks less than 6. Thick gives us the cumulative frequency of the less than type of 6. The cumulative totals of the frequencies obtained by proceeding from the top class of the table downwards are called the less than type cumulative frequencies. Similarly, if we add up the frequencies from the bottom class upwards, we get the cumulative frequencies of the more than type. We have given both these types in Table 6 for the data under consideration. For instance, the less than type cumulative frequency of 5 is 53. This means that 53 students scored 5 or less marks. Also, the greater than type cumulative frequency of 5 is 68. Thus, there are 68 students who scored 5 or more marks. From the table, we can also see that the number of students scoring above 5 but not above 8 is 96 minus 53 equals 43. We call the data presented in Table 6 grouped. This is because we have grouped together all the observations having the same value. We would like to mention here that the operation of grouping the observations is not unique. The grouping in Table 7 informs us that 35 students scored 6 or 7 marks in the test, but it does not give us the exact number of students receiving each of these marks. This shows that some information has been lost in this process of classifying observations into classes. Of course, as we have seen, this problem is avoidable in case of discrete variables by making each class correspond to a single value of the variable provided. The number of distinct values that the variable assumes is not too large, as is the case with example 6 discussed above. But summarization of data at the expense of loss of such information becomes almost unavoidable in the case of a continuous variable. In this case, if we take a class corresponding to each different value taken by the variable, then the resulting number I of classes will be unduly large. This approach will then look artificial since a I continuous variable, as you know, by definition is capable of assuming any of the values represented in a relevant interval. In such a case, we decide on the mode of classification depending on the nature of the data and the purpose of the study. Additionally, the following points are of help and can be taken care while deciding on the classes. 1. Each class should correspond to an interval of values of the variable. 2. The classes should be non-overlapping and exhaustive, i.e., an observation must be included in exactly one of the classes. 3. The number of classes should not be too small, since otherwise the actual nature of the distribution may be difficult to visualize and thus the summarization will fail to bring out the actual characteristics of the distribution. 4. The number of classes should also not be too large. 5. Classes should preferably be of equal width, since otherwise the frequencies of various classes may not be comparable. As a rule of thumb, the number of classes should be between 10 and 20 wherever the total frequency is more than 1000. Let us now take up the data in Table 3, corresponding to example 7 to illustrate the points made above. You may observe here that the smallest and the largest values are 511.6 and 1394.4 respectively. Note that here the values have been recorded correct to 1/10 of an hour. The life x hours of a bulb with 510.55 less than x 5.10.65 has been recorded as 510.6, the class 510.6. 590.5 actually includes all bulbs with life x hours satisfying 510.55 less than by 5590.55. While 510.6 and 590.5 are respectively called the lower and upper class limits, 510.55 and 590.55 are referred to as the lower and upper class boundaries. Similar is the case with the other classes. Once the classes have been determined, the frequency distribution can now be obtained exactly as before. The difference between the upper and lower boundaries of a class is called the class interval. The midpoint of a class is called its class mark. Thus, 510.55 plus 590.55, 2 equals 550.55 is the class mark of the first class. We can thus say that frequency distributions condense large sets of data and display them in an easy-to-understand form. Graphic methods are also used for presenting data and ideas. Graphical methods provide an effective way to present data as the give an idea of the pattern of variation of the random variable at a glance. We shall now discuss some of the more common forms of graphical presentation and see how they help us to illustrate, clarify and interpret the information contained in the data. 1.2.3 Graphical representation of frequency distributions. A frequency distribution relating to a discrete variable is commonly represented through either of the following two diagrams. 1. Bar diagrams. Fig. 1 gives the bar diagram for the data given in Table -7. Look at the screen. We can easily construct the bar diagram. Here the marks scored by TLY students are located on the horizontal, x-axis, and the frequencies of their occurrence on the vertical, y-axis. Note that the height of the rectangles, or bars, represent the club frequencies. From the heights of these rectangles you can easily deduce at a glance that am number of students scored between 4 to 5 marks. For convenience, we have at the top of each rectangle given the corresponding frequency. Asterisk. 2J frequency polygon. Another form of graphical presentation is the frequency P-Lygon. Frequency polygon for the data in Table 7 for which the bar diagram is drawn in Fig. 1 is SHO, KN in Fig. 2. Here the class frequencies are plotted at the class marks and the successive points are connected by straight lines. It is thus tacitly assumed that the frequency of a class interval is concentrated at its midpoint. Note that we added classes with 0 frequencies at both ends of the distribution to tie down the graph to the horizontal scale. In the case of a continuous variable, one often uses another diagram called a histogram. To draw the histogram of a set of given data, take a graph paper with rectangular coordinate axes and plot the class boundaries along the x-axis. Now over each class interval erect a rectangle the height of which equals the relative frequency of this class. The resulting figure is the histogram of the given data. Here we use class boundaries to demarcate the class intervals and not class limits. This ensures that there is no gap left between the rectangles. Thus, the area of these rectangles represent the frequencies of the corresponding classes. Fig. 3 gives a frequency polygon and a histogram for the frequency distribution of lives of 100 electric bulbs given by Table 9. Note that in Fig. 3 above we have plotted the rectangles by taking relative frequency of 18 a class along the y-axis. This histogram has the same shape as an absolute frequency histogram made from the same data set. This is because in both the relative size of each rectangle is the frequency of that class compared to the total number of observations. Presenting the data in terms of the relative rather than the absolute frequency of observations in each case is useful because, while the absolute numbers may change, the relationship among the classes may remain stable. Also note that if the width of the class intervals are the same, then the heights of the rectangles are proportional to their areas. Histograms and frequency polygons are similar. However, each one has some advantages. In the case of histogram I, the rectangle clearly shows each separate class in the distribution. E, the area of each rectangle, relative to all the other rectangles, shows the proportion of the total number of observations that occur in that class. For instance, looking at Fig. 3 one can easily conclude that normally, the lifespan of an electric BWLB is between 910 to 990 hours. Similarly, frequency polygon has certain advantages with I. The frequency polygon is simpler than its histogram counterpart. E. It sketches an outline of the data pattern more clearly. E. The polygon becomes increasingly smooth and curve-like as we increase the number of classes and the number of observations. Representation of a frequency distribution graphically on the basis of cumulative frequencies is also quite common. The diagram that one gets by plotting cumulative frequencies, less than type, against the upper class boundaries and joining the points by line segments is classed THK less than type O give of the frequency distribution. Similarly, one gets the more than type O give by plotting the more than type cumulative frequencies against Iowa class boundaries. Less than type O give for the frequency distribution of lives of 100 electric bulb given by TABLE9 is given in Fig. 4. Such figures are useful for finding how many measurements are located above or below a given point. Frequency distributions are often presented graphically as pie charts, where a circle is divided into sectors, pie-shaped pieces, which are proportional in size to the corresponding frequencies or percentages. To construct a pie chart, we first convert the class frequencies into percentages of the total number of observations. Then, since a complete circle corresponds to 360 degrees, we obtain the central angles of the various sectors by multiplying the percentages by 3.6. Fig. 5 gives a pie chart for the data in Table 7, giving the marks scored by 100 students in a statistics test. In this table you may observe that the total frequency is 100. Hence, the frequencies given by column 2 of this table also equals the percentage frequencies. Regions shaded differently in Fig. 5 represent these percentages. So far, we learned to construct tables and graphs using raw data. We see that the frequency distribution of a variable summarizes the statistical data on the variable and brings out the pattern and feature of its variation. But what if we need more exact measures of a data set? In that case, we can use single numbers, called summary statistics, to describe certain characteristics of a data set. For instance, how do you compare the performance of two batsmen in the game of cricket? You must have seen people saying that batsman 1 is better because his average score is better. Hardly you'll hear anybody making a match-to-match comparison. Thus, the average number of runs scored is a summary of all his scores in all the matches he has played so far. So in this case, average is the summary statistics that can be used to rate the performance of the batsman. We shall now discuss the summary measures that are commonly used to summarize information contained in a data set. 1.3 Summarization of data. The choice of a single number or summary statistics that we choose to summarize a given data depends on the particular characteristics we want to describe. In one study, we may be interested in the value which is exceeded by only 25% of the data. In another, in the value which exceeds the lowest 10% of the data, and in still another, in a value which describes the center or middle of the data. The statistical measures which describe such characteristics are called measure of location or measures of tendency. Some of such important measures are: 1. Measures of central tendency. 2. Measures of dispersion. We shall now discuss these measures one by one. 1.3.1 Measures of central tendency. If you take a close look at any data set, you would notice that though the manifestation of the variable is different for different observational units, the values tend to cluster around a central value. This property is referred to as central tendency. For instance, look at the data sets in Table 2 and Table 3. In these cases, at a first glance, the corresponding observations seem to be clustering around 6 and 1000 or thereabouts, respectively. A representative value around which a given set of observations tends to cluster, or equivalently be located, is a measure of central tendency or location, or is simply an average. Arithmetic mean, AM, median and mode are the three commonly used averages. Other averages are geometric mean and harmonic mean. Arithmetic mean. The most popular measure of central location is what the layman calls an average, and what the statistician calls an arithmetic mean, or simply a mean. The arithmetic mean is the sum of the numbers included in an irrelevant set of data divided by the number of such numbers. The median. Another measure of central tendency is the median. The median of a given data set is defined to be the middlemost observation or the mean of TKE2 middle observations. Depending on whether the total number of observations n is odd or even, once the observations are sorted in the increasing or decreasing order of magnitude. Thus there are as many values above the median as there are below. Median from ungrouped data. To calculate the median of a set of n observations, the n observations are arranged in the increasing or decreasing order of magnitude, and then, n plus 1, 2th observation is identified as the median whenever n is odd, when n is even, then the median is computed as the mean of the D2 and D2 plus 1 th observations. For example, suppose the number of road accidents on the first 5 days, i.e. Monday through Friday, of a week in a city was 2, 7, 4, 1 and 5. We arrange these observations in the increasing order as 1, 2, 4, 5, 7 so that the 5 plus 1, 12 thie. The third value, which is 4, is the median in this case. On the other HMD, suppose we also know that 3 accidents took place on Saturday in the same week, so that now we will have 6 observations which, when arranged in the increasing order, would look like 1, 2, 3, 4, 5, 7 and the median will be the average of the 6 halves, thie. The third and the 6 halves plus 1, thie. The fourth values, i.e. 3 plus 4, 2 equals 3.5. Now let us discuss the procedure for computing the median in the case of grouped data. Median for grouped data. For calculating the median from the frequency distribution, consider the data rat as represented in the frequency distribution of table 9. What are the exact OBSM and O tilde at IA? The class 510.55 to 590.55 or, in the next class 590.55 to 670.55. These are not known from the table. In fact, the individual OBSEW tilde TNs have lost their identities because of grouping, which has led to loss of such information. But, unless the observations are known, we cannot really manage them in order of magnitude. Thus exact calculation of the median in such cases will not be possible, and we have to find some way of estimating the same. In such a situation, one proceeds as follows. The first step in calculating the median from a frequency distribution is we find an arc tilde as interval that contains the median. To do this, we saint n with the lowest class INTQPD. Cumulate the number of measurements in 1, 2, 3 and subsequent class INTVDs. And stop with the interval where the cumulated number of measurements first exceeds or equals D2. This particular class interval contains the median. Let us illustrate what we have said above with the help of the data given in table 9. In this case, N2 equals 100 David 50. If you look in the column with cumulative frequency, less than type, then 50 lies in the 6th class interval. Since the cumulative frequency for the 5th class interval is 29 and for the 6th class interval is 55, it is clear that 6th class interval is the first where the cumulative number exceeds 50. Thus this is the class interval in which the median is located. Now to find the median M for the grouped data of this sort, we use the following expression: M equals N by 2 minus C divide by FM1 plus LM. Where C5 the number of measurements in class intervals below the one containing the median. FM equals the number of measurements in the class interval containing the median. 1 equals the width of the class interval containing the median. L equals the lower boundary of the class interval containing the median. For the data in table 9, N equals 100, C equals 29, F equals 26, 1 equals 80 and L equals 910.55, and hence using formula 4, the median is M equals 975.17. Before proceeding further with the discussion of another measure of central tendency, let us compare the uses of the mean and the median.
Uses of the mean and the median. Both the mean and the median are important and useful measures of central tendency. In some circumstances the mean is a better measure than the median, and in others the converse is true. The following factors contributes to the determination of whether the mean or the median should be used. 1. Sensitivity to extreme observations. The median is often preferred over the mean when the latter can be influenced strongly by extreme observations. Consider for instance, the computation of an average income of the families in an Apartment building containing 14 families, 3 of which earn Rs. 10,000 per month, 5 of which earn 12 rupees per month, 5 earn 15,000 rupees per month and 1 of which earns Rs. 1 lakh per month. Then the mean income per month in rupees of the 14 families equals 3, 10,000, plus 5, 12,000, plus 5, 15,000, plus 1, 0, divided by 1 4 equals 265 divided by 13 equals 18,929 rupees. However, this figure is not a very good description of the monthly income level of the majority of the families in the building. A better measure might be the median, which in this case is Rs. 12,000 per month. The median is much less affected by the 1 extreme value. 2. Open-ended class intervals. It may happen that in a frequency distribution some intervals do not have finite upper or lower limits. For example, in a frequency distribution of the monthly income of families, 2 class intervals might be less than Rs. 15,000 inches and 30,000 rupees and more. Each of these class intervals is open-ended. With such class intervals, there may be no alternative but to use the median, since calculation of the mean requires a knowledge of the sum of the measurements in the open-ended classes. 3. Mathematical convenience. The mean rather than the median is often the preferred measure of central tendency because it possesses convenient mathematical properties that the median lacks. For instance, the mean of 2 combined populations or samples is a weighted mean of the means of the individual populations or samples. On the other hand, given the medians of 2 populations or samples, there is no way to determine what the median of the 2 populations combined or 2 samples combined would be. 4. Extent of sampling variation. Sample statistics such as the sample mean or the sample median are often used to estimate the population mean. A major reason for preferring the mean to the median is that the sample mean tends to be more reliable than the sample median in estimating the population mean. In other words, the sample mean is less likely than the sample median to depart considerably from the population mean. You will be able to appreciate this consideration more when you study estimation later in Block 2. We shall now move forward and discuss the third measure of central tendency, the mode. The mode. Mode is defined as the most frequent observed value of the measurements in the relevant set of data. In a set of observations, if all the observations are distinct so that each of these occur with frequency 1, then it will be meaningless to say each of them is a mode. As such, in such a situation we say that the mode does not exist. However, from the definition, it is clear that a given data set may have more than one mode. For instance, if there are 2 modes, then the set of observations is referred to as a bimodal data set. In an interval grouped data set, the mode is estimated by the class mark of the class depicting highest frequency. In table 10, the score 5 appears with the highest frequency so that 5 is the mode of the scores of the 100 students. On the other hand, the mode of the data represented in table 9 is estimated as the mean of the 2 end boundaries of the class 910.55 to 990.55 as this class has highest frequency. The class interval containing the largest number of measurements is called the modal class. Thus, the modal class in table 9 is 910.55 to 990.55. For distributions which are symmetrical, that is, where the corresponding frequency polygons or histograms are symmetrical, mean, mode and median coincide. For slightly asymmetric distributions, it has been empirically found that mean minus median equals 1 upon 3 into mean minus mode, therefore mode equals mean minus 3 into mean minus mode. Uses of the mode. The mode, like the median, can be used as a central location for quantitative as well as qualitative data. If a printing press turns out 5 impressions, which we rate very sharp, and blurred, then the modal value is sharp. Like the median, the mode is not unduly affected by extreme values. Even if the high values are very high and the low values very low, we choose the most frequent value of the data set to be the modal value. Also, mode can be used even when one or more of the classes are open-ended. However, the mode is not used as often to measure central tendency as are the mean and median. Too often, there is no modal value because the data set contains no values that are repeated more than once. There may be cases when every value occurs the same number of times, or the data sets contain 2, 3, or many modes. In such cases, the mode is not a useful measure. A measure of central tendency, as has been mentioned above, gives us a general idea about the average value or the magnitude of the observations. However, two distributions through may have the same mean, say, may differ in respect of several other characteristics. For instance, consider the following data which relate to performances of two suppliers. A manufacturer of a certain electrical equipment purchases 100 cardboard boxes for packing purposes every week from each of two suppliers A and B. And the following are the two distributions of defectives in the weekly lots. Look at the screen. Observe that both the suppliers have supplied 6 defective boxes on an average per week. Judging from this aspect alone, we may be tempted to conclude that both IHE suppliers have performed equally. However, a closer look at the distributions reveals that this is not really so. While the number of defectives supplied by varied widely between 0 and 14 over the weeks, the performance of B has been more or less stable and consistent. The number of defectives supplied by him being more or less around 6. This suggests that the extent of variation or dispersion of the given sets of observations from the respective averages together with the averages themselves can give us a much wider scope for comparing the performances. Similarly, suppose that the average score obtained by students in 10 marks class test is 5, and suppose it is further known that the scores varied between 3 and 6. With such information in view, one can predict his performance with much more coincidence than one when the scores are known to have varied between 2 and 8. These examples suggest that the average along with an idea about the scatter or spread of variation or dispersion of the observations about the average give us a more complete picture about the state of affairs than the average alone. Thelius as the range, the more will be the concentration of observations around the mean. We shall now discuss as to how the dispersion of the observations about the average can be measured. 1.3.2 Measures of dispersion or variation. There are two types of summary measures of dispersion: distance measures and measures of average deviation. Distance measures describe the variation in the data in terms of the distance between selected measurements. The most frequently used distance measure is the range. Range. It is defined to be the difference between the largest and the smallest observations. In the above table, the range for A is 14 minus 0 equals 14 and that of B is 8 minus 4 equals 4. The range, because of its complete dependence on two extreme values, is a quick but not a very accurate measure of dispersion. For instance, both the sets of observations, set 1 to 1, 1, 1, 1, 1, 1, 1, 1, 1, 10. Set 2 is to 1, 10, 10, 10, 10, 10, 10, 10. Have the same range, namely 10 minus 1 equals 9, but, evidently, the distribution are very different. Significant measures of average deviation are variance and the standard deviation. Both of these tell us an average distance of any observation in the and a set from the mean of the distribution. 1.4 Summary. In this unit we have covered the following points. To study a given phenomenon, any physical situation, the basic raw material is the data, information, relating to it. 2. Statistics involves the collection, organization, analysis and interpretation of data. 3. A collection of data is a data set and a single observation from a data set is the data point. 4. For a data set to be useful, observations need to be organized in order to pick out trends and come to local conclusions. 5. The number of times any value occurs in a data set is the frequency of that value. 6. An organized display of data showing the frequency of each value in a data set against its value or against mutually exclusive classes into which these values fall is a frequency distribution. 7. A tabular display of data showing how many observations lie above or below certain values is a cumulative frequency distribution. 8. Graphical methods of presenting data provide an effective way to present data as it gives an idea of the pattern of variation of the random variable, character, corresponding to numerical value, at a glance. 9. A histogram is a graph of a data set, composed of a series of rectangles, each proportional in width to the range of values in a class and proportional in height to the number of items falling in the class. 10. A line graph connecting the midpoints of each class in a data set, plotted at a height corresponding to the frequency of the class as a frequency polygon. 11. Augev is a graph or a cumulative frequency distribution. 12. Single numbers that describe certain characteristic of a data set are summary measures. 13. Summary measures that are commonly used are measures of central tendency and measures of dispersion or variation. 13. A measure indicating the value to be expected of a typical or middle data point is a measure of central tendency. Mean, mode, median are such measures. 15. A measure describing how scattered or spread out the observations in a data set. R is a measure of dispersion. Mean, deviation and variance are such measures. 16. Mean is a central tendency measure representing the arithmetic average of a set of observations. 17. Median is the middle point of a data set, a measure of location that divides the data set into values. 18. The value most often repeated in the data set is the mode. It is represented by the highest point in the distribution curve of a data set. 19. In a data set, the average distance of the observations from the mean is the mean deviation. 20. In a data set, the average of the square of distance of observations from the mean is the variance and its positive square root is the standard deviation. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.